Hi and welcome back to DATQVAULT video lectures. In this video we're going to cover a bunch of different kinds of alkene reactions that might pop up on the DAT exam. First reaction that we're going to look at is epoxidation, which is basically the addition of an oxygen atom across an alkene using a peroxy acid. The next reaction that we're going to look at is hydrogenation, which is the addition of hydrogen across an alkene to reduce it to a simple alkane using a catalyst such as palladium or platinum on carbon. Third reaction that we're going to look at is a hydroboration followed by an oxidation. In this reaction, we're going to add an OH to an alkene with the use of borane and then a peroxide and base to get an anti-Markovnikov addition of an alcohol across an alkene in a syn fashion. The last reaction that we're going to look at with alkenes is an ozonolysis reaction, which is the use of ozone and then zinc to basically break an alkene in half and add a carbonyl to each side of the alkene. Alright, so there are quite a few important reactions that we're going to learn in this lecture and try to understand. So definitely feel free to watch this video more than once if necessary to be able to grasp all the concepts in it. Also, if you feel the need to stop and rewind them if something really isn't clear, I highly suggest doing that as well. Alright, so we're going to go over epoxidations first of alkenes. So we'll go over a couple different examples. Epoxidation of an alkene is the addition of an oxygen atom across a carbon-carbon double bond. And this is usually achieved by using different kinds of peroxy acids. Here we're adding an oxygen across this alkene using a peroxy acid called MCPBA. We'll take a look at the different peroxy acids a little bit later. Here we're adding an oxygen across the double bond of this cyclohexene using another kind of peroxy acid called PAA. Notice that both of these peroxy acids are interchangeable, and also during an epoxidation reaction we get the addition of the oxygen across the double bond in a syn fashion, which means the oxygen is added to the same side of the double bond, giving us syn stereochemistry. Common peroxy acids that are used for the epoxidation of alkenes are peracetic acid, also known as PAA, which looks like this. And another very common one that you might see on the DAT is MCPBA, or metachloroperoxybenzoic acid, which looks like this. Again, both of these peroxy acids can be used interchangeably, and you might see either of these on the DAT. So, what's the mechanism of epoxidation, and why do we get syn stereochemistry from the epoxidation reaction? So here's an epoxide, here is a peroxy acid. In this case we're going to use PAA. We get the name peroxy acid because we have this oxygen-oxygen single bond, which is a fairly weak bond, and because of this weak bond it's going to be a very reactive molecule for an epoxidation reaction. So we get syn stereochemistry, which is the addition to a single side of an alkene, because the epoxidation reaction happens entirely only on one side of the alkene. And that's because since we're reacting one molecule with this planar alkene, and the fact that the reaction is going to be completely concerted, the reaction can only happen on one side of the alkene at a single time. So what the reaction arrow pushing mechanism looks like is the electrons in this carbon-oxygen carbonyl double bond are going to come out and they're going to remove this hydrogen from the oxygen of the peroxy acid. The electrons then in this bond are going to attack one of the alkene carbons, and then the electrons in the alkene are then going to come out and attack the oxygen bearing the hydrogen and the oxygen of the peroxy acid. The weak oxygen-oxygen bond of the peroxy acid is going to break, and those electrons are going to donate into the other oxygen-carbon bond. Notice again that this reaction is going to be completely concerted, and this reaction can only happen on one side of the alkene at one time, which leads us to have syn addition of this oxygen atom to the alkene. Once the reaction is completely done, we get the carboxylic acid as a byproduct, and we get the addition of the oxygen atom to the alkene on a single side of the molecule. Alright, so just a take-home message for this reaction: it's completely concerted, and epoxidation of alkenes goes by syn addition. Alright, let's look at the hydrogenation of alkenes, which is the addition of hydrogen across a double bond, reducing the alkene down to a simple alkane. This reaction is achieved using a catalyst such as palladium on carbon, and you'll also see this reaction done with platinum on carbon. So with an atmosphere of H2 and our catalyst of choice, we can reduce this alkene, even dialkenes, trialkenes, doesn't really matter. As many alkenes are in the molecule that will be reduced, they'll all get reduced down to a simple alkene. Alright, so here's another more complicated example of the reduction of an alkene by hydrogenation. In this case, we are forming two different stereocenters. This reaction is meant to highlight the stereochemistry of addition of a hydrogenation reaction, which is, again, like the previous reaction, going to be syn addition, which means both of the hydrogen atoms are going to be added to the same side of the molecule. I have here that we also form the enantiomer of this molecule. That's because the hydrogens can be added to the alkene from either the top side or the bottom side of the alkene. In this case right here, if everything is flat facing us on the screen, then these hydrogens have been added from the back side of the alkene. The enantiomer would be the hydrogens added from the front side of the alkene, and both of these substituents here, the methyl group and the ethyl group, would then be facing back. So why do we get syn addition of hydrogen across an alkene? It's basically for the same reason as for the previous reaction that we looked at for the epoxidation reaction, is that the whole reaction is going to be concerted, which means it has to happen on the same side of the double bond. So here we have our surface of either palladium or platinum, and then when we add hydrogen to this reaction, palladium interacts with the H2 molecule in such a way that it's going to coordinate to the bond, and it's going to basically weaken this bond. Once this happens, then our molecule that contains an alkene is then going to come into close proximity with this H2 molecule that has now been, I guess, kind of activated by palladium. One side of this molecule is going to come down, get close to this hydrogen molecule, and then the electrons from this hydrogen-hydrogen bond can come up and attack one of the carbons of the alkene, and then the double bond of this alkene will then come down and I guess attack the other hydrogen of the hydrogen molecule. This whole reaction is going to happen on only one side of the alkene, which gives us syn addition of the hydrogen across this alkene double bond. Alright, the next reaction that we're going to look at is going to be a hydroboration, then followed by an oxidation reaction. Here we have an alkene that has four different substituents on it, if you want to count this hydrogen right here as a substituent. The first step in a hydroboration oxidation reaction is the hydroboration step, so we're going to use borane, and THF is a common solvent for this reaction. This might seem a little bit complicated, so pause the video if you need to take a chance and kind of understand what's going on in this reaction. Here we're adding the boron to one of the carbons, the least substituted carbon, and then the hydrogen, one of the hydrogens on borane is going to be added to the more substituted carbon. So this is going to be an addition of borane in an anti-Markovnikov fashion. If it was the Markovnikov addition, then the boron would be added to the most substituted carbon, but that's not happening in the hydroboration step. Also, notice that the hydrogen and the boron are being added again to the same side of the alkene. So again, this reaction goes by syn addition. We also get the enantiomer from the addition of hydrogen and boron to the opposite side of the alkene. Alright, so the next step is the oxidation step. The oxidation of this molecule is going to occur with the use of peroxide and base. If we add these two reagents, then we're going to get basically a substitution of the BH2 substituent for an OH. So overall, with the hydroboration oxidation, we're going to get the addition of an alcohol to the alkene in an anti-Markovnikov fashion. Also notice that once we do the oxidation step of this reaction, we get retention of stereochemistry and we do not get inversion, which means the alcohol is still going to be syn to the hydrogen that we previously added. So there's no inversion of stereochemistry between this molecule up here and our final oxidized molecule. So why do we get syn addition of the boron to the alkene? Basically the same reason for the past two reactions, which were also syn addition. The entire reaction has to happen on one side of the molecule because it's completely concerted. So if we look at the arrow pushing mechanism of this reaction, we have to know that boron has an empty p orbital, and so the electrons in this alkene double bond are going to attack this empty p orbital of boron, and then the electrons in the boron hydrogen bond will attack the most substituted carbon. Boron will go towards the least substituted carbon just for electronic reasons in this case. Alright, now we have the anti-Markovnikov addition product of the boron to the alkene. Also we have the syn addition product. Hydrogen and boron have now added to the same side of the alkene. The next step is the oxidation step, which is actually a more complicated mechanism than we're going to get into and something that you're not likely to see on the DAT. Just definitely the take-home message from the oxidation step is that you have retention of stereochemistry, which means that OH group is going to end up being on the same side of the molecule as the previous BH2 group in this case. Okay, so the last reaction that we're going to now look at is going to be the ozonolysis of alkenes. Again, this reaction kind of has a complicated mechanism and it's something that you're definitely not likely to see on the DAT. But we want to know from this reaction what the products look like because ozonolysis is actually a very, very common reaction. So in ozonolysis, we just use O3 followed by zinc to cleave any kind of alkene in half to get two different carbonyls. So basically you're just taking this alkene and you're adding an oxygen to either of the carbons of the alkene. If we do ozonolysis to a tethered alkene, such as a cyclohexene molecule, we're not going to get two different molecules out of it, like the example above. Instead, we're going to get a single molecule that has two carbonyls attached to it. Again, this might be a little bit complicated to see, so why don't you take a second maybe and draw this out, pause the video, or go back and just take a second to work through how ozonolysis works and why we get the molecules that we get here. Alright, so let's do a practice DAT question that kind of encompasses everything that we've learned. So why don't you pause the video for a second and work through this example problem and then we'll go through it together. Alright, so if you read through this problem, you notice that there's not really a whole lot of stuff that you can work through. It's pretty much just rote memorization unless you remember the specific mechanisms for each of these reactions. So definitely the takeaway message from all these reactions that we learned today, with the exception of the ozonolysis reaction, is that all these reactions go by syn addition. So the answer to this question is actually going to be E, all of the above. Hydrogenation, epoxidation, hydroboration, oxidation all go by syn addition, which is the addition of the atoms in the reaction to the same side of the alkene. So I do realize that a lot of this material can be really dry at times, but you just have to find some way to make it interesting, or you're not really going to have a great time in graduate school. So um, not every topic you learn in college and during dental school is going to be really an interesting topic. So you need to find ways to keep the material basically fresh and intriguing to you. So um, to help you out with this, when trying to memorize, for example, countless organic reactions, such as the ones that we just learned, such as these, uh, we actually designed some reaction trees for you guys to help you learn all these different organic reactions. So I suggest that you actually check them out. They're on the website. I think they're really helpful, and I actually think they're really fun. So check those out, and also make sure to do the practice quizzes and to do the practice problems that are designed to help you out with each of these lectures, and really solidifying all the ideas in these lectures that will help you out on the DAT.